Okay. So, what I will do is now use finite difference method to solve PDEs. Of course, finite difference method is used for many things, including ODEs, derivative calculations, okay. But we will use it to solve PDEs, partial differential equation, right. Everybody knows full form of PDE, no? PDE, partial So, there are many partial differential equations, linears and nonlinear, diffusion, Navier-Stokes, Schrodinger, okay, nonlinear Schrodinger, Burgers, KdV. So, there are thousands of them, but we will take some and we will optimize them by different techniques, MPI, OpenMP, GPU. So, let us see how we use parallel computers for solving finite difference PDEs using finite difference method. Okay, so, as I said, I will do 3 kinds of problems as projects: finite difference method, MD, molecular dynamics, which is particles, basically particles under force, and Monte Carlo method. So, I recommend that you can get hold of this book, because method you will find it here. I will not dig deeper into finite difference method. I just give a sketch for one problem, but we will use Navier-Stokes. So, some details you will find in the book. If you look at the Kindle version, it is cheap, it is around 69 rupees, lowest price. Okay. So, let us look at briefly what FD method is, finite difference method. So, I am going to solve this equation. So, in general we will have a PDE of this form. So, we have phi, which is function of position and time. I am using 1D right now, but it could be 3D, 4D, 2D. Okay. So, it has 2 independent variables, x and t. So, you will find that equations of PDEs are of this form. Well, not all equations, okay. This is called parabolic form. So, wave equation is different, it is a double derivative in time, no. So, we are not going to solve wave equation in this course. Okay. So, we will just focus on some set kind of equations. So, this parabolic form equations, and we are assuming that the space derivative, these are space derivatives, are only up to second order. You can do third order, fourth order, but let us assume we stick only to this order. So, I am doing 1D. So, first at a given time I discretize my variable in space. So, in this room there is a temperature field, velocity field, it is a continuous variable, no, velocity field is every x, but in computer you can't store at every x. So, say well I am store at a discrete points in space. So, just look at it here, I discretize this into n points, starts from phi 0 to phi n minus 1, and these are locations. For this course we will choose the distance between these two neighbors as constant, equidistant points. Okay. So, if this length was L, so delta x will be L by L. Okay. So, normally these PDEs will have boundary condition, like in this room the velocity is 0 at the walls. Okay. So, we will have a boundary condition. So, this one is an example where I am choosing a vanishing boundary condition. So, this phi is 0 at both ends, okay, or it could be periodic boundary condition. That means, this phi 0 is same as phi n minus 1, n point adjoined. Okay. So, I am going to discuss that periodic boundary condition, how to implement it in a program. So, once you discretize these points, then I can solve these phi's not for every point in space, but at those discrete points. So, what happens to this equation? It is a PD, but now I am going to solve evolution of this phi at the grid points. So, let us look at this phi 2. So, I can say I equal to 2 d by dt, and I compute the right hand side, this one at point 2. Okay. So, imagine this function is phi minus phi plus this right hand side, okay, this f. So, what do? I know the function at this point phi which is phi 2, but double derivative. So, double derivative I can use any method, you know. So, double derivative, what is the double derivative at this one? So, one method gives you that phi I plus 1 minus 2 phi I plus phi I minus 1, is that correct? Minus 1, yeah, divided by 2 delta x square, if I get it correctly. Okay. So, this is the formula. So, if I have the discrete points, then I can compute the derivatives. So, my f I is computed, then I can. So, how many differential equations will I get now? One great advantage is that PD has been converted into ODE, right, and ODEs are easier to solve than PDs. So, normally in numerical methods you will find that PDs are converted to ODEs. Okay, so, we convert to ODE, and now I have n ODEs for every point. If the Vanishii boundary condition, then we do not want to time advance this one, these two, they remain the same as 0, 0 will remain 0, but then I am time advancing these values. Okay. Got it? So, I have n minus 2 equations, differential P ODEs, and I time advance them. Okay. So, this is a t equal to 0, t equal to 0. So, I have n points. I am ignoring right now this subtlety of boundary condition, and I just go from at time t to time t plus delta t. So, this time index in my book, I use this notation n within bracket, this one, and this is a t plus delta t. So, n is used for time index, understand. So, at what level in time. So, n equal to 0 means the initial condition, n equal to 1 is delta t, n equal to 2 is 2 delta t, and so on. You can also safely use delta t to be constant. There are times when delta t is not constant. In fact, there are advantages of not choosing a constant delta t. For this course, we are focusing on HPC. So, I am not worried too much about this great scientifically accurate code. You are worried about how to speed up a code. Okay. So, this is the objective of the course is speeding up a code, not accurate code. Okay. So, so this is Euler method, right? Everybody knows about Euler method. So, this is at time t. So, if you can write this as phi t plus delta t is phi at I, okay, I t plus delta t times right hand side f I t. Okay. So, this is translated here, I am indexing is with n. Okay, you are right, f has n index at time t, yes, for Euler, yes. Well, Euler forward, yeah, good, thank you. Okay. So, there is let us solve it for diffusion equation is an illustration. So, the double derivative is, well, there is 2 missing, 2 is incorrect, this is the correct formula, there is no 2. Okay. So, this is the formula for the double derivative. Okay. Kappa is the diffusion coefficient and h is the distance between 2 neighboring points, delta x. Okay. So, this is my right hand side is f I of t or f I of n. Okay. So, this is computed at time t. This is Euler method. sorry, no, this is no Euler method. This is right now the differential equation ODE. Okay. Now let us try to solve it in a real Python code. So Euler method will be I time step. So n to n plus 1, the time difference is delta t. So kappa RHS times delta t, which is we just multiply this by delta t. Okay. Euler is not accurate. So I am going to illustrate for using Runge-Kutter's second order. Okay. So this is the code in the book, and also I am sharing this is the with Colab for the course. So let us just focus on, there are some subtle points. Okay. So I am using it for a periodic boundary condition. Okay. Just for, you can use vanishing, but I am using for periodic. I want to use vectorized operation, otherwise loop will be slow, right. Of course you can use NUMBA as well, but vectorize is the code is short and it will give the same speed up as NUMBA. So I have these points, n points. So the notation I follow, which is there in many textbooks as well. So my data points are 1 to n minus 1, 1 to n actually, 1 to n. There are n data points, 1 to n. Okay. So my Python array starts from 0, right. It is always, you can't change Python array indexing. So there is a point sitting here. The point sitting, I will make another point which is sitting beyond n. So I will create an array of n plus 2 dimensions. So always add 2 points. Why add those 2 points? Because my boundary is sitting here, or basically you say, well, to compute the derivative here, I need the data in the left as well if I use second order scheme. So if I want to compute the first derivative at phi of 1 d by dx, what will that be? Phi 2 minus phi 0 divided by 2 delta x. I recommend that you should at least use second order, do not use first order. Okay, second order is okay, not so great, but is at least second order. So I need this value at the left. For periodic boundary condition, this value should be equal to what? This one should be equal to phi n. So I am going to set phi 0 equal to phi n after I do this update the variables. And what about this value? I need that for computing derivative at n. So that should be phi 1, right. So this should be, so you imagine that this is looping, this is looping down. So neighbor of n will be 1, right neighbor, periodic boundary condition. So this is phi n plus 1 equal to phi 1. So we set this, then we have periodic boundary condition. Okay, so let us look at this stuff. So I have created an array f. Why is it loading? Okay, I think it's cut paste. So f is n plus 2 dimension array. For RK2 I need an intermediate array. Okay, RK2 we go to the midpoint, then from midpoint I make the jump from 0 from first point to the next point in time. Okay. So that is one, and as I said, this region is updated with the initial condition. Okay. So it could be exponential function or Gaussian function, whatever. Initial temperature, typically it is good idea to take initial temperature to be something like that. Gaussian, there is a heater in the center. Okay. Heater which is turned off, keep it hot, then turn it off. If you keep the heater on, then the diffusion equation is not correct, right, because they need a source. So I set this to initial condition, but now I need to do this. So f0 equal to, okay, initial temp is an array, okay, which is size n, not n plus 2. So the last value is, so this is basically phi n, okay, this one, and this one is phi f n plus 1 is this value. So, this is basically initial temperature is size n array. Now, it is a loop, n steps is the number of time steps I am going to work with. How many time steps I have used? So, okay, so I am going up to n steps plus 2. So, ignore that part y plus 2, this is some subtle reasons. So, just focus on this one. I go to f mid. So, RK2 if you recall, RK2 goes from, so I want to go from here to here. So, this is t equal to 0 to t delta t. So, I compute the slope here and go to the midpoint delta t by 2. Okay. So, I need to project to delta t by 2, then compute the slope again at delta t by 2, and using the slope, that slope I jump from 0 to delta t, that is RK2. So, first go to the midpoint by Euler method, then use the central difference, central point to go from 0 to delta t. Okay. So, this is a step. So, I go to the first midpoint. So, here it is prefactor is the right hand side, I put a 2. So, delta t by 2 is coming here, this 2, and you can look at it here, these all vectorized, 1 to n plus 1. So, this is 1 to n plus 1, this part is 1 to n plus 1. Okay. By the way, this is index is n plus 1. Okay. Is it index 1 plus 1 plus 1? Yeah. So, in the Python index is n plus 1, they will give you n, index is 1 less. So, this is the thing. So, I just update it with RHS, which is, this is f at I, this f I plus 1 and this f I minus 1. Now, this is shifted. So, this is doing vector operation. So, it is not every point I, is doing, you should think of set of arrays, you shift the array to the left, that will be shift adding I minus 1. So, I minus 1 I just shift it by 1. So, it is 0 to n. So, 0 to n will be, this is the tricky part, 0 to n is this. Okay. So, for 1 I am going to use this number, the left number. For 5 I use 4 by when I do this, but it is going to be vectorized, in one shot is going to do it, and this is fast. If you do using a loop, it will not get speed up. Okay. This is the current location f I, and this is I plus 1 which is shifted to the right. Okay. So, this is going to the midpoint here in time, is the midpoint in time. So, this is the value of the temperature at time t plus delta t by 2, t plus delta t by 2 by Euler fast forward, Euler forward scheme, and I need to adjust this endpoints. So, what do? I just copy it here. Okay. Minus 1 is the endpoint. Minus 1 is same as the last point, which is this last point is this one. Okay. So, now I compute this at I know do this jump now. So, which is n plus 1 equal to f n plus 1, which is what. So, this is a later time, a t plus delta t, and this is the right hand side computed at the mid. Mid is an array. Okay. Mid is the temperature, projected temperature at t plus delta t by 2. Okay. So, my answer right now will be f, after this my temperature this f 1 to n plus 1 is my answer at t equal to t plus delta t. Before the loop it was at t plus at time t. So, I made advance in 2 steps. So, I recommend use RK2, but for testing you can use Euler. First time use Euler, but once your code is tested you can use RK2. Is it clear? So, this is what you should use for vectorized operation. Now, this is a single sequential core, sequential code. Now, of course, it's 1D, but if I have 2D, then what do I do? So, 2D straightforward, no problem. I will have Laplacian. So, I will have Laplacian, no? Laplacian of phi will be, in Cartesian it is this. So, I will have derivative along x and derivative along y. So, no problem, for derivative along x we already done this. I just go sideways along x, but for along y I do the vertical direction, derivative along vertical direction. Same idea, for y j will be varying, for x I will be varying. Okay, you just add up. So, this will look slightly complicated, but just try to do it properly. Okay, is that clear? 3D is very similar, we will have one more Laplacian, so we will have k direction. Now, all this is in sequential code, single core, but if I have, what if I have more than one core? Let us focus on 2D. So, I may have 1000 cores, I want to use them to speed up my code. So, the first problem you will encounter is this. So, intuitively what will I do? I divide the data into two parts along x direction. So, my data is divided along x direction like this. So, the first processor P0 keeps data 0 to 3 columns. The second one keeps 4 to 7. Equal division, great, very good. With this I can compute derivative along y direction, everybody can compute derivative, no problem. But now x direction, this derivative can be computed, right, because I need the data in the left, data in the right, second order, okay, central difference scheme. But if I, what if I want to compute derivative here? Then what should I do? I need a data in the right hand side which is not available in the processor P0, right, it is the problem, right. So, I need to copy the data in processor 0. Okay. How much data do we need to copy from P1? How many columns? Just one column. Okay. For central difference, one column is enough. So, I need to take this column and push it here. Well, I make another column in P0. So, P0 will have one extra column. Okay. What about P1? Does it need the data from P0? It needs the data, no? For example, I want to compute derivative here, then I need this data. So, this data should be shared, should be copied into P1. Now, I am not worrying about this part. Periodic boundary condition means this guy should be same as this guy. So, I need to copy the left wall as well. So, I am just giving you an illustration, but if you let us say 4 processors or 1000 processors, then my processors are divided like that, and all this data has to be shared from both left and right. So, there will be left data and right data to be shared in 2D. For 3D you need to share slabs. Here in 1D, 2D, sorry, 3D you need to share slabs, in 2D you need to share columns. Okay. So, this picture tells you that the overlap region. So, the overlap region has to be shared by both. So, the processor 0 should contain 0 to 4 and processor 1 P1 should contain 3 to 7, 5 columns, ignoring the left side. Okay. If it is periodic, then we need to worry about it. If it is not periodic, then it is okay. Vanishing is fine. We do not need to worry about the going to the right. So, this is what we need to do. For parallel computing, this sharing is important for finite difference, and also this is called load balance. So, data should be shared equally among all. It is not that one processor is given only 2 columns, the other processor is given 10 columns. So, why is it bad idea? The 10 columns will take longer time, and this has to finish together. I mean, you can't say one student will do more work. Well, in a project, everybody should do equal work, and so then the project will complete in time. Okay, so this is what basically you need to worry about this part, and other than that time advance is straightforward, no, Euler or RK2. Once you have the derivatives computed, then you can use time advance at every point. So, it is a ODE at every point once I have the derivatives, and I can solve it using RK2, RK3, RK4. Okay. So, the problems which I would like to be solved in this class is compressible hydrodynamic equation. I should forgot SD. So, there is something called continuity equation, which is, so fluid has several variables. So, we have density, right, in this room, velocity field, pressure, okay. There is also temperature, okay. So, there are 6 variables, okay. So, but we will focus on, okay. So, let us see. So, we need six equations. So, first equation is called continuity equation, which is for the density, okay. You can derive it from first principle, mass conservation, okay. So, this is the equation. Second one is momentum equation, which is for the velocity field. So, here is the pressure and mu is the viscosity, okay, dynamic viscosity. The right hand side has some Laplacian divergence. You can see all of them are derivatives, right, space derivatives. So, how many equations we got so far? So, in 3D you will have 4, right, this is 3 equations and 1 equation. Okay. So, we do a trick for this course, we will do a trick. We will not write equation for temperature. So, this variable I will get rid of, but I will give you equation of state. Okay. Assume ideal gas. So, ideal gas is anyway P equal to rho RT, but in addition you assume an equation of state. So, you can say temperature is constant, okay, that is isothermal approximation, or very commonly used is pressure is rho to the power gamma times constant, right. This is a polytropic assumption. So, this is always there, okay. So, this is always there. In addition, you use a polytropic assumption. So, temperature can be always determined once you have the these two conditions. So, given density I can find pressure, and once I know pressure, then I can find temperature. So, temperature we will get rid of in this course, because we have one more equation otherwise, and use equation of state. So, we have 5 equations, 5 unknowns and 5 equations, and this is not a ODE, this is not a time advanced equation, this is a constraint. So, pressure is function of density, and we can use rho to the power n, not n is a variable, okay. Often is used as for adiabatic approximation, n is gamma, Cp by Cv. So, this is one project. So, shall we stop here, and because anyone has a class right now? Yes, 10:30. Shall I finish this part? I will take 5 more minutes. Okay. So, this equation 1, then we will have incompressible, this course will not work, but here there is a constraint called del dot E is 0, and there the pressure is not coming from equation of state, it comes from a Poisson equation, okay. But this course I will not assign this project, but this equation is very difficult equation to solve, okay. We will keep our course simple for this semester. So, Poisson equation is okay solver, but it is slightly complicated, not very difficult, but it is slightly complicated. Schrodinger equation everybody knows, everybody likes that equation, right, quantum. So, this one equation. So, given initial condition you can solve potential. There is something called non-linear Schrodinger equation, it is called Gross-Pityevsky equation. So, there is a new term called G mod psi squared times psi, okay. It is a non-linear, it is a effective equation for superfluids, superconductor, Bose-Einstein condensate, okay. So, you can solve this equation. So, let us discuss a bit more on finite difference method. So, for a single CPU I showed you how to do it, right. I mean basically PDE, we are solving PDE, we need to compute the space derivatives, and that we use by finite difference. However, if when the data is huge, then we need to use more than one processor. Okay. So, the idea which we discussed in the last class was we divide the data among many processors, but there is a problem for processor P0. It needs data of at least some columns in the of P1 and vice versa. Okay. Now, in distributed memory system, distributed means the data memory this data is private to each processor, and if needed they will send part of the data. Okay, that is called distributed memory system. So, in distributed memory system we have to do this send receive, which I am going to discuss it a bit later after the midterm exam. So, this P0 and P1 need to talk, and we need to write several lines of codes in addition to sequential code, which is a pain. No, I mean you have to write this send receive, you keep track what to send, what to receive. Okay. The simpler option, if your data size is not too big, and if you can put it in a single system, okay, then what should you do? You can use OpenMP or shared memory architecture. Okay. If you shared memory, then we do not need to. So, the full memory is shared by all the processors. I may use 8 processors of my CPU, or I can use 200 processors of a CPU. Nowadays, there are machines which has, so ROM, right, ROM or the next version of AMD machine has a CPU has 128 cores. I can put 4 of them. So, you have something like nearly 500 cores, 512 cores. So, 512 cores can act on this shared memory, and we do not need to do this send receive. You can access any memory. Okay. So, OpenMP has advantage. The code rewrite is very small compared to sequential, and it is convenient. Okay. Now, however, in one node you cannot, I mean you can put maybe terabytes of data, but sometimes we have really big data set. So, right now the highest record for fluid simulation is 32,000 cube. Okay, it is very big, that will not fit in single node. So, we do need to send it to distributed systems. Okay, then what do I, well, one option is to just okay. So, you should notice one option. So, each node, this is a node, and there is another node. So, for simplicity let us assume there is P0, P1, P2, P3. So, if I do MPI with distributed memory system, I can assign 4 different memory for these 4 processors. Though this is in one system and this is another system, it is called system 0, system 1. Okay. But well, there is a clever option that okay, why do I want to distribute, I mean cut memory, send receive for the processors within a system. I may use OpenMP to keep the P0, P1 should be sharing the memory of system 0, and P2 and P3 should be sharing memory of system 1. So, this is called hybrid parallelization. So, I will be using OpenMP within a node, but MPI across the nodes. Okay. So, it is slightly more complicated, but this is also done. Okay. Now, this is the CPU, but turns out with GPU will be very fast if you use single GPU. So, if I have GPU, they can use finite difference solver, and it will be, I mean it could be several thousand times faster than a single core. But GPU has memory right now maximum around 100 GB, single GPU. So, that is a bottleneck. You can't really do a very big grid, but for many applications 100 GB is very good. Okay. For 2D problems we can go up to 4, maybe around 20,000 squared or even 40,000 squared. Very big grids can be obtained in a single GPU. But if you need more data, then there is a node. We discussed that in the past. A node has more than one GPU. In fact, NVIDIA has a node which has 8 GPUs. Okay, this is called DGX box. And this box you can use all 8 of them. There is some memory communication between them. So, you can do this send receive across the GPUs, but this is a very fast machine. Okay. And now, you most likely will manage most applications in a single DGX box, but if your data does not fit in single DGX box, then what should I do? Then I have to use 2 DGX box or 10 of them. Okay. So, there are machines with 1000 DGX boxes or 1000 of this GPU servers. Okay. In India, CDAC has a machine which has 64 of these DGX boxes. Okay. So, anyway, so this is what we need to plan. So, what do you want, MPI, OpenMP or GPU? Okay. Depending on your need, you should choose one of them.